All right, we've talked about exponents and powers and applying and calculating with exponents, and now we're going to kind of expand that and apply that to what we call scientific notation. And scientific notation is a way to write very large or very small numbers using multiples or powers of 10. So just to give you an idea of what we're talking about here is I've got a couple examples here of many different ways I can write the same number and write it as a product of a number and a multiple of 10. So on the left-hand side, I just have the number 6,500, and I can write the number 6,500 as the product of two numbers, 650 times 10. Would you agree? 650 times 10 is 6,500. So I can write this number as a product of a number and a multiple of 10. Or I could write it as 65 times 100. Notice that the first factor got 10 times smaller and the other factor got 10 times bigger. So I went from 650 down to 65, and I went from 10 up to 100. And I can continue this. I can make this 10 times smaller and the other one 10 times bigger. I can write 6,500 as 6.5 times 1,000. That's also 6,500. Or I could write 6,500 as 0.65 times 10,000. So another way I can write this number as a number times a multiple of 10. In the other column, I've got another number, 125. I can write 125 as 12.5 times 10. I could also write it as 1.25 times 100. Or I could write it as 0.125 times 1,000. So lots of different ways I can write numbers as a factor times a multiple of 10. Okay, so only one of those is what we call scientific notation. Now, scientific notation uses powers of 10 and factors to write very large or very small numbers, but we have to follow specific rules, and I have those highlighted right here. Scientific notation is a number that is written as the product of a factor and a power of 10, but the factor must be greater than or equal to 1 and less than 10. Okay, so it cannot be less than 1 and it cannot be greater than or equal to 10. So we write it as a times 10 to some power, where a is greater than or equal to 1 and less than 10. So we call that scientific notation, and that's a number expressed as a product of a factor and a power of 10. If you do not write the number using exponents, that's called standard form. That's where we write the number without using exponents. And there are a couple examples right here on the screen of both standard form and scientific notation. 3,500,000 is in standard form, and then on the right-hand side, we write it as a number times a power of 10. That's equal to 3.5 times a million, or 3.5 times 10 to the sixth power. 1 million is 10 to the sixth power. And we can also write very small numbers here. Here we have 0.00004, which is tenths, hundredths, thousandths, 10,000ths, 100,000ths, 4 100,000ths. And that's equal to 4 times 10 to the negative fifth power. Remember that negative powers mean that the number is very, very small. Doesn't mean that it's negative. So just a review of what those negative exponents mean. So again, another review of our powers of 10. Okay, up to 1 million being 10 to the sixth power, 100,000 being 10 to the fifth power, 10,000 is 10 to the fourth power, 1,000 is 10 to the third power, 100 is 10 squared, 10 is 10 to the first power, and 1 is 10 to the zero power. Notice that powers of 10 greater than 1 have a positive exponent, and those are the numbers that are up here in this blue box. Okay, greater than 1, the exponent is going to be positive. And then in the lower box, I have 1/10 or 0.1. That's 10 to the negative first power. 0.01 or 1/100th is 10 to the negative second power. 1/1000th is 10 to the negative third power, and so on as we decrease in value. Again, these are getting smaller, but they are still positive. Okay, so then these indicate numbers that are less than 1 but greater than 0, and they're going to have a negative exponent. So when we have a negative exponent in our scientific notation, we're talking about a very small number. If we have a positive exponent in our scientific notation, it means a large number, or at least a number larger than 1. So again, writing numbers using powers of 10, I'm doing the same thing now, but now instead of writing out the multiple of 10, I'm writing it in using exponents. So here I use the number 7,000. I can write the number 7,000 in several different ways. I can write it as 700 times 10 to the first power, or 700 times 10. I can write it as 70 times 10 to the second power, or 70 times 100. I can write it as 7 times 10 to the third power, or 7 times 1,000, or I can write it as 0.7 times 10 to the fourth power, or 0.7 times 10,000. Now I could go on and on and on here, but I just wanted to show a few examples here. Now only one of these is actually considered scientific notation. Can you tell which one of these 4 is the scientific notation of 7,000? It is this one right here, because that factor has to be between 1 and 10. All of these other factors are not between 1 and 10. These two are too large and this one is too small. So this one here is considered the correct form of scientific notation. Next one here, I wrote a decimal number, 0.25, as a product of a number and a multiple of 10. We could write 25 hundredths as 2.5 times 1/10, or 10 to the negative first power. We could also write it as 25 times 10 to the negative second power, or 25 times 100th, or 250 times 1,000th, which is 10 to the negative third power. Now, which one of these 3 is the correct way to write 0.25 in scientific notation? If you said the first one, you would be correct, because again, that factor has to be between 1 and 10. 2.5 is between 1 and 10. These others are too large of factors. So we have to write our scientific notation in a very specific way. We have to make sure that that factor is between 1 and 10. So let's practice here. I've got some numbers, a couple large numbers and one small number, and we're going to write these as a factor from 1 to 10 times a multiple, or a power of 10. So 900, where would I have to place my decimal in order to make this number between 1 and 10? Well, I'd have to place it right here to make it 9.00. And it was here originally. That means it's moving 2 places. So I can think of this as 9 times 100, or 9 times 10 to the second power. Since I moved the decimal 2 places, that's going to tip me off as what my exponent is. 9 times 10 to the second power would be the correct way to write this in scientific notation. Next one, 18,900. Where would I have to place the decimal to make this number between 1 and 10? I would have to put it right here and make it 1.89. 1, 2, 3, 4 places to the left. So I'm going to write this as 1.89 times 10 to the fourth power, since I moved my decimal 4 places. And the last one, where would I have to place the decimal to make this number between 1 and 10? It would have to be right here between the 6 and the 4. And I would move the decimal 1, 2, 3, 4, 5 places. And remember, this is a very small number. So it's going to be 6.4 times 10 to the negative 5th power, since we're talking about very small numbers, numbers less than 1, but greater than 0. So pretty straightforward ways to find your exponents on your powers of 10. Just check how many times you move the decimal. And again, if the number is larger than 1, you're going to have a positive exponent. If it's smaller than 1, you're going to have a negative exponent. Now we're going to go the other way around. We're given numbers in scientific notation, and we have to write them in standard form, or without an exponent. So 4, my decimal is right here. So since this is going to be larger than 1, I'm going to move the decimal 2 places to the right, and then basically fill those spots in with zeros. So 4 times 10 to the second power is equal to 400 in standard form. Next one, 5.94 times 10 to the 7th. If I write my 5.94, I'm going to move this decimal to the right again, because this is a much larger number than 1. So I'm going to make it larger. 1, 2, 3, 4, 5, 6, 7 places to the right, a lot of students will just add 7 zeros to the end of the number, but that's incorrect. You're moving the decimal 7 places, not adding 7 zeros. So this number is actually 59,400,000. Okay, you can see that scientific notation is a much shorter way to write this number, and that's why it's used. And then the next one, 1.3 times 10 to the negative third power. Since that's a negative exponent, I know this number is going to be less than 1. So I'm actually going to be moving my decimal to the left 1, 2, 3 places. Fill in those zeros. So this is actually 13/10,000ths, or 0.0013. Again, a much smaller number than 1. So that's how we can go both ways, writing standard form or writing in scientific notation. How do you compare numbers that are written in scientific notation? Here I have a couple of them, 6.3 times 10 to the third power and 4.1 times 10 to the fourth power. How can we tell which number is greater? Well, the 6.3 is larger than the 4.1, but the power of 10 on the left is smaller than the power of 10 on the right. So which one is actually larger? Well, if we write these numbers in standard form, 6.3 times 10 to the third power is 6,300, and 4.1 times 10 to the fourth power is 41,000. Well, here it's easy to see that the one on the left is smaller. So I know that 4.1 times 10 to the fourth is a larger number. So what is actually going to tip us off on what number is larger? Is it the factor or is it the power of 10? It's actually the power of 10. So how to compare numbers in scientific notation? The first thing you want to do is compare the powers of 10. The larger exponent is the larger number, period. Okay, if 1 has a larger exponent, you know it's automatically bigger because all the factors will both be between 1 and 10. 2, if the exponents are the same, then compare the factors. The larger factor is the larger number. So your first line to look at is the power of 10, and then secondly, look at the factor to determine if the powers of 10 are equal. So let's look at an example here. Approximately 1.372 times 10 to the 7th square kilometers of Antarctica, and about 1.834 times 10 to the 6th square kilometers of Greenland are covered by an ice cap. Which landmass has a greater area covered by ice? So again, I have these numbers rewritten here in scientific notation. Which one of these two is larger? Well, again, the first thing I want to look at is the exponents. Which one has the larger exponent? Antarctica does, so that means that this is the larger number. So Antarctica has a greater area covered by ice. So scientific notation, writing very, very large or very, very small numbers as a factor between 1 and 10 times the power of 10, and then comparing numbers in scientific notation, always looking at that exponent first, and then looking at the factors if the exponents are the same.